function generators and oscilloscopes and multisim. So we're going to need a function generator. So we go to our right-hand toolbar with all of our devices on it. Previously, we used it to get a multimeter. The top button. We go to the second button down. That's our function generator. So we'll go ahead and click that and replace our function generator. And then we'll go ahead to the same toolbar, fourth button down, the oscilloscope. So just to go over function generators and oscilloscopes and multisim. Function generator. Remember that ground is located in the sources. Ground reference, remember that ground is located in the sources group, the power sources family. So to get there, I just went to the upper left toolbar there with the components. Replace source. Make sure it's in power sources family. And we can pull the ground component there. Replace that. So first, I'm going to check our reference voltage. So it's a common terminal on the function generator. That's what connects to our reference voltage. In this case, it's ground. And then our oscilloscope, we're going to be using channel A. So I'm going to go ahead and take the negative terminal for channel A, connect that to our reference ground voltage. And now the positive terminal on the function generator is what's actually going to output the function voltage. So we're going to connect that to our positive scope terminal. The negative terminal on the function generator, that's really just used for generating the inverse function of whatever is output on the positive terminal. We're really not going to be using that much, so I'm going to leave that alone for now. That's just what that does. So we'll be using just the positive terminal and the common terminal. They will be connected like this. You want to connect it directly to the scope just if you want to see the raw output of this function generator. And to see that, we can double click the oscilloscope. That'll bring up the scope window. Resize it however you want. I go ahead and run the simulation now. The default settings for the function generator are being used. We haven't changed those yet. So down here at the bottom of this window, the scope window, there's your time base section, and then here you have channel A, channel B. So just going to go over function generator. Down here at the bottom of this window, scope window, there's your time base section, and then here you have channel A, channel B. In the time base section, we can change our time scaling. Right now, it's at 10 milliseconds per division. Divisions being just these grid lines here. So one division would be, grid line to grid line. That's one division. Right now it's set to 10. Milliseconds per divisions, we can actually crank that up to, let's say, 500 milliseconds per division. And if I go ahead and pause the simulation, you can get a look at this signal. So if I just take 2 points on this signal to measure distance between, let's say, this peak here and the next peak, this distance here, which is one full cycle of the signal, the distance here is 2 divisions. So one full cycle of this signal is 2 divisions at 500 milliseconds per division. So we know that this is about 1,000 milliseconds or 1 second period for this particular signal, meaning that it has a 1 hertz frequency. And in terms of voltage, we can see that peak to peak, our low point here is negative 2 divisions. 2 divisions below the 0 axis. And then our high point here is 2 divisions above our 0 axis. So from this low point to the high point, that's 4 total divisions times 5 volts per division, that's 20 volts. From this low point here to the high point. So, and then you can also change voltage scaling. You just go to, let's just say 10 volts per division, and now that same 20 volts still the high point is now 2 divisions, but it's at 10 volts per division, 10 times 2, 20 volts. So now going to the function generator itself to adjust the settings, I double-click the function generator and I'll bring up this little window. And so we can select from different waveforms. If I go ahead and run the simulation, we can switch to triangle wave, switch to square wave, or back to sine wave. The frequency we can change here to, let's just say, double. And now you can see the wave. Oscillating twice the frequency. For the amplitude, we're going to come back to duty cycle in a second, but for the amplitude, we measured it to be 20 volts from peak to peak. From the low to the high point. But it says 10 here, and that's because this is really what that number is saying, is we have 10 volts from our 0 point up to our highest voltage is 10 volts. So, and conversely, the point the voltage from 0 to our lowest point is also 10 volts. But that's what this number is. Just keep that in mind when you're setting this number. This number is essentially double in terms of peak to peak voltage, from the low to the high. Like 20 volts, or double what you have in this amplitude box. The offset just shifts the signal up and down. So I can go ahead and run the simulation some more. If I set the offset to 10 volts, you can see it shift up by 10 volts. And then if we were to set it to negative 10 volts, you would see it shift down. So let's set that back to 0. And now to duty cycle. Sine waves don't have duty cycles. They are a consistent shape. The only thing that affects the shape of a sine wave is the frequency and the amplitude. Other than that, it's all pretty constant. But triangle waves and square waves have duty cycles, and I think duty cycles are covered later in voltage is. If I pause the simulation, duty cycle is just going to change how wide this top part is of each cycle and how narrow the low parts are. You'll see that when I change this, let's say 80%, now we can see that the peaks are very wide, the lows are very narrow. If I go the opposite direction, 20%, the peaks are very narrow, the lows are wide. For a triangle wave, it just affects how skewed. You'll see what I mean when I change this, how skewed triangle is, left or right. If I set this to 80%, now you can see it's kind of skewed to the right. So the signal is rising for a longer amount of time than it's falling. Like go the opposite direction, the opposite happens. Now it's left. So now it's rising for a very short amount of time and taking a while to fall back down. So that's all that duty cycle. Kind of just changes the shape of the triangle and square wave. And then in terms of, so I'm going to stop the simulation now. In terms of rise and fall time, so set rise fall time button. Rise and fall time is, let me just get a square wave back. We'll go ahead and pause it. So rise and fall time just means how long does it take to go from this low point here to the high point. That's rise time. Fall time is how long it takes to go from high to low. So right now it's at 10 nanoseconds, which is a very, very, very short interval. And because our time scaling is so large, 500 milliseconds per division, we don't really see a rise or fall difference in it. Just a vertical line. If we were to increase this to, let's say, let's try milliseconds. Now you can see it's much more pronounced. It's taking 100 total milliseconds to go from this low point to the high point, and that's taking 100 milliseconds to go from the high point down to the low point. Let's change that back to nanoseconds. And now back to basically vertical. So that is how you manipulate the function generator. So this lab here, lab 1, calls for a 0 to 5 volt pulse at 500 ohm resistor. That pulse, we would set function generator to, and it doesn't specify frequency, so I mean you can just make it whatever. 2 hertz is fine. Probably makes it easier to see. Makes it easier to track signal. cycle, not specified either. So, and for the most part, we're going to be 50%. Nice, even square root. The amplitude, it does say that it needs to be 0 to 5 volts pulse. Meaning it's a pulse that goes from 0 volts to 5 volts, back down to 0, and then back up to 5. So the way we're going to manipulate these numbers is by using amplitude and offset to do that. So when it says 0 to 5 volts, the amplitude we're actually going to set to half of that peak that we want, 2.5 volts. Because we want the total distance from the low point to the high point to be 5 volts. Actually, go ahead and change our scaling, scaling as well. Just say 2 volts per division so we can see that better. And actually, no, it's 5 volts per division. And so you can see the waveform is now 5 volts from the lowest point to the highest point. And now let's change the offset because we don't want it to go from negative 2.5 to 2.5. We want to go from 0 to 5. So we're going to have to offset it by another 2.5 volts. And that will give us our 0 to 5 volts oscillating signal. So that is how we use the function generators and how we use the scopes.